The last lesson of the unit is lesson 8 on exponential growth and decay. So exponential relations and their graphs can be used to solve problems in science, medicine, finance. The ability to analyze data and model it using exponential relations is important for making accurate predictions. So the formulas for exponential growth and decay look like this. You might use different variables, but this is basically what the equations would look like. When we're talking about exponential growth, we would have a plus sign, meaning that the rate, something would be increasing. And if we have exponential decay, something is decreasing, like the value of a car over time or something like that, we would have a minus sign in the formula. Otherwise, anytime you see a little subscript of 0, that's always initial. So this would be the initial amount, this would be the final amount. We would have a rate of growth or decay, but we always want to make sure we use a decimal. And n is the number of growth or decay periods as our exponent. Some common questions that you might see, we sometimes talk about doubling. If we're looking at bacteria or cells and we talk about doubling being an example of exponential growth. Doubling time is the time it takes for a population to double in size. So inside the bracket of our formula, we would have 1 plus. So the 1 means like the amount that you started with as far as 100% of what you started with, plus another 100% if it's doubling. So our bracket might look something like that. And therefore inside this bracket here, we would end up with a 2 if it was a doubling question. Half-life is also a common example of exponential decay. The half-life of a radioactive substance is the number of hours it takes for half of the initial amount of the substance to decay. So the number is constant regardless of the initial amount of the substance. If you had a half-life question, inside the bracket we would have a 1 minus the amount, and if our amount is being cut in half, we would use 50%. So inside our bracket, we would end up with 0.5. Something less than 1 is showing you that the amount that you started with, which was 100%, has gone down or decreased. So let's just look at how to use this formula. Example 1, a bacterial culture began with 75,000 bacteria. Its growth doubles every 36 hours. So we have sometimes this concept of a cycle. So one cycle is 36 hours long. Let n represent the number of bacteria and t the doubling periods. So if I had my formula, maybe n would be my final amount. We would have an initial amount, and then we could just change the variables, although it doesn't really matter too much what the variables are to represent. So what we do know is that we start our initial amount, the little subscript of 0, we started with 75,000 bacteria, and we know that it went up by 100% because we are talking about doubling, so we would do 1 plus 1, and then our exponent, if it doubles every 36 hours, how many bacteria would be present after 36 hours? Be careful there. That means that the exponent would be 1. So 1 cycle is what we would have, 1 doubling period. So we just have to be careful with exponents. We often follow BEDMAS. If you have brackets on your calculator, you could just type this in as you see it. But we would have 75,000 times 2 to the exponent 1, which is just 2. So we end up with 150,000 bacteria. And that should make sense. If they double every 36 hours, in 36 hours, that's 1 cycle, they should have doubled. So if we had 75,000, now we have 150,000. And the formula, is one way to do it, but it also is sort of common sense. If we have 72 hours, 72 divided by 36 is 2. So we actually have 2 doubling periods. So in this case, our t would equal 2. Our initial amount is still 75,000. We are doubling, so 1 plus 100%. And then our exponent is 2 this time because we have 2 doubling periods. So if we think about this using BEDMAS, we could do 75,000 times 4. which gives us 300,000 bacteria. If it doubles once, we go up 75,000 to 150,000. Then when it doubles again, it doesn't just go up by 75,000, it goes up by another 150,000. And then if it doubled again, it would go up by 300,000, which is maybe why you can kind of imagine that this would be an exponential curve. So the next question says, find the half-life of radium-224 given that 0.8% of the substance decays in 1 year. So 0.8% means 0.008. If I was talking about a decimal, I always have to divide my percents by 100. So imagine moving the decimal place twice to the left. This doesn't give us a lot of information. It doesn't give us the initial amount or the final amount. So we can just replace that with 100% of the substance. So let's just use the number 100 for the initial amount. And then if half of it decays, we lose 50% of it. The final amount would then be 50. If you're not given an amount in grams or something like that, we're able to use 100 for our initial amount, and we know we'd end up with half of that. So our formula for exponential decay, our final amount is 50, our initial amount could be 100, and then we know that it's decreasing by 0.8%, so 0.008. But what we're trying to find in this question is how long that would take. If I simplify this a little bit, I could maybe look inside my brackets first. 1 minus 0.008 is 0.992 to the exponent n. I could also maybe divide both sides by 100 so that I'm just trying to eventually isolate the n. So I have 0.5 equals 0.992 to the exponent n. So this is saying 0.992 to what exponent gives 0.5. So when we're trying to find an exponent, we know that we can use logarithms. We could write that in logarithmic form, where the exponent is what we're trying to find, and we have a base of 0.992. The answer is 0.5. But we're trying to figure out what the exponent would be. So on my calculator, usually I don't have that type of button, so I would do the log of 0.5 divided by the log of 0.992 on my calculator, and I would get 86.3. So therefore, the half-life of radium-224 is about 86.3 years. So we know that if you started with 100%, it would take about 86.3 years to end up with half of that. Example 3 is a different kind of question. Jacques bought a new car for $15,000. Each year, the value of the car depreciates by 30% of the previous year's value. When will the car have a value of $500? Again, we're looking for when. How long is it going to take? So I feel like we're going to have to find out what the exponent is again. The initial amount is our little subscript. The initial amount is $15,000. The final amount is $500. We also have a rate of 30%, so our R is going to equal 0.3 because we always want to use the decimal form and make sure we divide that by 100. And I know to use the exponential decay formula where I have a minus sign here because the car is depreciating in value. So anytime something is going down in the amount, we would always use the decay formula. So our final amount is smaller than what we started with, and I sub in everything that I know and I simplify. I could divide both sides by 15,000, And then I could use fractions. I end up with 0.0. I'm going to use a few decimal places to make sure I'm accurate. And then 0.7 to the exponent n on the right. So if I want to find out the number of years it's going to take for this card to depreciate to $500, I'm going to have to find out what my exponent is. So we're saying 0.7 to the exponent what gives us 0.03333. I don't know what n is, but I could write this in logarithmic form. So remember, my base is 0.7, so that's my subscript. My answer is 0.03333, rounded off, and then I'm going to find out what the exponent is. And because my calculator doesn't have a button with the blanks in it, I'm going to have to type in on my calculator the log of 0.03333, and I could put more threes, divided by the log of 0.7. And if I round it off, I get about 9.5 years. So it will take about 9.5 years for the card to depreciate to $500, given that it's depreciating at a rate of 30% per year. So you can also imagine that it might start to decrease really quickly, and then it does kind of slow down year after year, just like a decreasing exponential graph would look. Example 4, the last one, a colony of bees increases, okay, so that's an exponential growth formula, increases by 25% every 3 months. So how many bees should be bought if a farmer wants to have 10,000 bees in 18 months? So this is one, it's not just going up once a year. We are increasing by 25% every 3 months. So we need to figure out the number of growth periods that we have, or the number of cycles. So 18 months, but we are going to go up by 25% every 3 months. So we have 6 cycles, or 6 periods, growth periods. Our final amount is 10,000 bees. So the farmer wants to have that in the end. But our initial amount, how many bees should be bought? This time we don't know our initial amount. So just be careful there. If we don't know our initial amount, the A subscript 0, that is what we're trying to find this time. So I would fill in my equation. I know we're increasing by 25%, so 0.25. I do know the number of growth periods is 6. So my goal is to isolate the initial amount. I might simplify further on the right. I see that 1.25 to the 6 is about 3.814697. If I round it off, I'm trying to leave quite a few decimal places just to be accurate. I could divide both sides by that. So I end up with the initial amount being 2,621.44. This means that the farmer should start with around 2,622 bees in order to end up with 10,000 in 18 months, because they are growing exponentially at a rate of 25%.